Hello everyone. Today we will be talking about content from Chapter 7, which is accounting for the rate laws, and today we will be talking about elementary reactions. In this particular case, our special category is the unimolecular reaction. And our in-class exercise was focusing on cyclopropane. And it has molecular structure, which is a strained ring system, which if we put on our organic chemistry caps, we would know is highly unstable because of our bond angles. And when this particular molecule interacts with another cyclopropane molecule, it can actually degrade into propene, and propene is described by this structure. In this particular case, we know that in order to react, we will have an intermediate which precedes product, which I'll just call big P, formation. Okay. So let's go ahead and set up this reaction. And so we're basically saying that our species A goes to products, but we need to break down all of the individual steps. And so we've got a forward reaction, which is a collisional reaction of two molecules of our cyclopropane, which are described by rate constant K1, which then forms A and A star being our excited intermediate. We also have our intermediate step for product formation, which includes our excited state complex yielding our products described by K sub 2. And then we also have our reverse reaction, which is the de-excitation reaction. So this is another collision of an excited state molecule. And after we have our collision, that energy is transferred, and we start off with our reactants. Two molecules of unexcited A, and we can deem this the de-excitation pathway. You'll notice that the rate of formation of our product can be described by that intermediary rate, which was K2 A star. Now, A star itself is a short-lived intermediate and is unstable. So if we form it, we either immediately go to products or we immediately go back to our reactants. And so right now we're going to introduce a new concept known as the steady state approximation. And this is very important. And the general idea, mathematically, is that the change in the concentration of our excited state intermediate as a function of time will be equal to 0. And so right now what we need to do is merge our rate equation with this general assumption for a change in the concentration of A star being equal to 0. And so we're going to set up our equation and link everything together. And so we have our equation, that is K1 is equal times the concentration of A times the concentration of A, which is our conversion to excited state, minus K sub 3 times the concentration of A times the concentration of A star, minus K sub 2 times the concentration of A star. And let's go ahead and write down what each of these represents. This is our conversion to the excited state. Then K sub 3 represents the conversion back to reactants, or what we called our de-excitation. And then we have K sub 2, which is our conversion to products. So now we've set up our equation, and we're going to algebraically rearrange and solve for the concentration of A star. And you should take paper and pen and go through the individual steps in order to yield the same representation as I have. And after you've rearranged and solved for A star, you should yield K sub 1, the concentration of A squared, over K sub 2 plus K sub 3 times the concentration of A. And since dP over dt equals K sub 2 times the concentration of A star, our product formation, or dP over dt, can therefore be represented by K sub 1 times K sub 2, A squared, K sub 2 plus K sub 3 times the concentration of A. Overall, the way that we can describe this is that this equation is the solution for product formation using the steady state approximation for a unimolecular reaction. So right now what we need to do is to apply two limiting cases based on our mathematical representation. And the first one that we need to deal with is at high pressure. So at high pressure, A star, our activated complex, becomes deactivated quickly due to collisions. And so what we would say is that K sub 3, our deactivation rate, is much, much greater than K sub 2. And in that particular case, we need to look at the condition in which our product formation, dP over dt, is now going to be equal to K sub 1, K sub 2 over K sub 3 raised to the first power of the concentration of A. And what we need to look for, and with paper and pen you should yield the same mathematical equation. I want you to do this, but the take-home message is that in the case of high pressure, first order of kinetics dominate for this case. Now, if this was kind of confusing, I think what we need to do is go ahead And very quickly over here in the corner, rewrite dp over dt equals k sub 1, k sub 2, a squared over k2 plus k3a. Now, if in this particular case we end up having k2 go to 0, we can't go ahead and say that k2 is equal to 0 because then we have a non-trivial solution. But if we go ahead and get rid of that, we'll then have k1, k2, a squared over k3. We can then go ahead and simplify, get rid of one of our units of a, and we would then yield k sub 1, k sub 2, the concentration of a over k3, and you'll notice that it agrees well with what we have at the top. Okay, our next scenario is at low pressure. And at low pressure, A star concentrations are maintained, and K sub 3 is much, much smaller than the rate of product formation, K sub 2. So let's go ahead, write up our product formation equation, and see what happens if we have K3 being much, much smaller than K2. And as you recall, this is our form of the equation. Now K3 being so small, that would go to 0, yielding then K1, K2 times the concentration of A squared over K2. We can then simplify, get rid of K2, to yield K sub 1 concentration of A squared. And in this particular limiting case in which A star is maintained as an intermediate, you'll notice that we now have second order rate kinetics. And so if we were to double the concentration, we would quadruple the overall rate of formation. And if we were to triple it, then we would increase it by an order of 9. And so you can see the power of this representation, where we can actually understand how the rate order changes under different conditions. So I wanted to make sure that we did a little math check here for our product formation, dp over dt, in case there was any confusion on how we yielded our final representation. And so let's take a step back and make sure that we understand that the concentration of A star was equal to K sub 1 A squared over K2 plus K3 times the concentration of A. And from here, what we do is we apply our definition for dp over dt equals K sub 2 A star. And so what we're going to do is make sure, once we substitute in our value for A star, that we go ahead and we substitute in and algebraically rearrange for that value. And so after doing the substitution, you'll notice that we have 1 over K sub 2, which we need to get rid of. And in order to get rid of that, we're going to multiply by K sub 2 over 1 to this side of the equation. And we're also going to multiply the other side by K sub 2 over 1. That, of course, eliminates our K sub 2's on the left-hand side. And on the right-hand side, we then get K sub 1, K sub 2 times the concentration of A squared over K sub 2 plus K sub 3 times the concentration of A. So our little sanity check, make sure that as you go over this particular mathematical proof or derivation that you yield the same representation. And that is the end for our unimolecular accounting for the rate loss. Thank you very much.